The obvious extension to our discussion of transitions within an atom and how they produce spectral lines is to consider the ultimate case where instead of having a bound transition, we have a transition which moves from a bound state to a free state. The electron is no longer bound to the atom. So let's develop how that works out. And to do that, we'll want to just take a step back and recall what we already learned about oscillator strengths. Let me share my screen so that we can get going. Okay, now recall that we related oscillator strengths to the Einstein coefficients. And we related the situation of, say, the Einstein coefficient VUL for an emission oscillator strength. So this is where we have an emission photon, a photon emitted rather than absorbed. And that's related to 4 pi e squared over h nu, and this is from the lower to the upper state times mc times the oscillator strength from the upper to the lower state. And because we know how to relate our statistical weights for various transitions, we know that the statistical weight of the lower state times the lower times upper is just equal to the negative of the upper times the statistical weight of the upper to the lower. So emission oscillator strengths are negative. And we can then write the A coefficient in terms of the emission or the absorption oscillator strengths. And this comes through as G upper to A times A upper lower is equal to minus 8 pi squared E squared nu upper lower squared over MC cubed GU FUL. Or we can write it in terms of the opposite transition, which produces an absorption oscillator strength. And that just is the same set of equations, but we reverse which oscillator strength we're using. MC cubed, and this is times GL FLU. But it's meaningless to talk about the oscillator strength from one level to another level if instead of dealing with from one level to another level, we're dealing with from one level to a free state where it's at an infinite range of different levels. And so with this in mind, we have to think about how can we just make the next bit of transition to consider what energy range we have transitions for and to what energy range of continuous states. And to do that, let's just write this whole set of relations in a slightly different way. So generally for hydrogen, we can write the oscillator strength times some statistical weights as, let's take the initial times the final state, so GFI final. And it's written, you can derive this yourself as the same from all of our previous relations, but it's easier for me to just write it out for you right now. It's the initial times the final cubed, the Gaunt oscillator strength. And you may recall our Gaunt factors from our free emission discussions. Well, instead of free, this is bound free that we're going to be discussing here. And typically G Gaunt is approximately equal to 1. Okay, so from there, for bound free situations, we let the final energy level, NF, be replaced with a term that's the imaginary times the wave number, so I times k, the wave number. And then if we were to write out our energy level for energy level n, which is in general 1/2 alpha squared mc squared over n squared, then if we replace n with ik, then we end up with 1/2 alpha squared mc squared over k, which is just equal to 1/2 mv squared, which is clearly very obvious that instead of having a discrete energy level set by the nth level of the electron, we're setting it to a free electron, and its energy is set by its kinetic energy, which is 1/2 mv squared. So the change in energy for the system from the bound free state to its free state is 1/2 mv squared plus chi of n, which is the ionization potential, or the ionization energy, I should say, from the nth level. Now the statistical weight Gi for the initial level is 2n squared. And from here we can, I should not say the statistical weight, I should say the G factor there, derive this Fnk, the oscillator strength, or Fnk, sorry, that should be Fnk, which is taking us from level n to a free state, which is our k state. So Fnk, the oscillator strength, is 32 over 3 pi times the square root of 3, 1 over n to the 5th power, k to the 3rd power, g gaunt over 1 ni squared plus 1 over k squared, and all of that cubed. We can go from there to defining the frequency, the angular frequency, and that's 1/2 alpha squared mc squared z squared, where this quantity here is just the Rydberg constant times z squared over 1 n squared plus 1 k squared. And that allows you to see that the frequency of that transition, the angular frequency of that transition, is equal to Rydberg constant times whatever the z is for the ion times over n squared plus 1/2 mv squared. So that tells us, based off of our previous estimates, that this must be the ionization energy from the nth state. So we can work from there and show that there's a cross section. Now recall that the absorption coefficient is equal to the number density times a cross section in a general sense. So this is a general, and we did this back in week 1, I believe. So the bound-free cross section works through to be related to the Einstein coefficient is approximately equal to the initial final B coefficient times h bar on omega, where that's the omega initial final. And this can be written instead as 8 pi times 3 root 3 c h bar to the 6th z to the 4th power over n to the 5th 1 over omega cubed times g gaunt. And this is the photoionization cross section. So that says that for an atom sitting in a radiation field, what cross section does it present to that radiation field at the likelihood of becoming entirely ionized? Now, if omega is greater than the ionization energy over h bar, then it will be equal to 1/2, which is equal to 1/2 alpha squared z squared mc squared over h bar n squared. So for z equals 1, the bound-free cross-section is 6 × 10⁻⁻18, oops, that's squared, not cubed, per square centimeter at the threshold energy. Now this is useful for considering how much photoionization you have in a system given a single radiation field. We can actually work this the other way around to consider the free bound cross-section. So that's the recombination cross-section. So that says that for a set of ionized hydrogen, what's the cross-section, the likelihood that we're going to actually recombine that atomic hydrogen? And that's what happened in the early universe. That's what happens is regions around H2 regions start cooling down. There's a lot of places in astrophysics where that happened. So you can use detailed balance, and this may end up as, for example, a homework problem, to show that the bound free over the free bound cross-section, the ratio of those two is equal to m squared c squared nu squared over nu squared h squared times the statistical weight for the electrons, the statistical weight for the ionized gas, over 2 times the statistical weight for level n. And that presents the number of recombs. It allows us to figure out the number of recombinations per unit time, per unit volume, in a velocity range dV. So that's dN, that's number of recombs, over dt dV per unit time per unit volume is on the order of the density of the ionized gas to the density of electrons, and density, the ion density to the electron density, I should say, which may be equal, times the cross-section of the free bound cross-section times a Maxwellian distribution of velocities times the velocity of dV. And what you find from that is that the recomb rate goes as 1 over T to the 3/2 power, which is to say that cold gases recombine more quickly than hot gases. And that sort of makes sense if you think about electrons that are very hot are moving around very quickly, and they're not necessarily actually coming close enough to be bound into an atom. But if you slow them down, you move the gas more slowly, and then you can consider binding those into atoms more readily. So the fact that recombination occurs at all is why we have a universe as it is now today, and the recombination was an important part of that. So we'll stop there, and we'll move on finally to discussing line shapes in our next lecture.